it's almost embarrassing to make a project out of it. And that's what it should be, right? I mean, the math is very complicated, but you don't need to know or care about that. They just need to write a Python library you can use, and that they have done. So here's the summary, which you've already talked about. This is a quantum-resistant key protocol, now approved by the government, or sort of provisionally approved, you know. It's considered the best, and they took it seriously enough. They have told everybody you should start moving towards it. So Alice runs keygen to generate a key. She generates a public and private key. The public key is called the encapsulation key, and the private key is called the decapsulation key. She sends the public key to Bob. Then Bob runs the encaps algorithm, which produces his copy of the shared secret, along with an associated ciphertext to send back to her. So I think they haven't said it here, but I think it must have included him adding something, a random number here. So he sends that ciphertext back to Bob, or back to Alice, and Alice uses the decaps algorithm, combining her private key and the ciphertext, and she now creates a shared secret, her copy of the shared secret. Bob can take the encapsulation key and make his copy of the shared secret. So they both have now agreed on the same shared secret, and this stuff that was sent across was not easily related to that shared secret. So it's and that logic, it's all the same. So this is all you got to do, and this stuff works in Google Colab. So let me put it in there, and you'll see that's why the original demonstration was just like 5 commands, and that's all you need. So I just added the missing pieces here to make it sort of more reasonable for a project. So and by the way, you don't have to go download it from GitHub or anything. It's now included in the standard library, KhyberPy, which is nice. So that'll install it. There we go. It's installing KhyberPy. And now all we have to do is run the algorithm. We're doing the 5.12 version here, which I think is the lowest security version. So we do the keygen, and that creates an encapsulation and decapsulation key, which is her public and private key. So I printed them out, and you can see the public key is 800, the private key is 1632 bits long. And I just printed the first 20 characters of it in hex just so you can get a clue what it looks like. And then Bob gets the shared secret by just running encaps on the encap key, which is what she sent over. And so that creates a shared secret and a ciphertext to send to Alice. And so shared secret is only 32 bytes. I think these are bytes, 800 bytes, 832 bytes. Yeah, I think they are. Not bits, but bytes. So he has 32 byte shared secret, and he sends this ciphertext to Bob, and Bob uses Alice, and Alice uses her key and the ciphertext to do the decaps algorithm, and that creates the same shared secret at this end. So now they both agree on this shared secret, starting with 95. Now, like I say, you could use that as the key, but that would be considered unprofessional. It's not expected to be used in that manner. What you're expected to do is treat it like a password and generate a key from it with a key derivation function. So that's what happens here. And we've done this before. We're going to use AES because there's nothing wrong with AES. AES remains secure even in a quantum world. The most you'd have to do is make the key longer, but only up to 2 reviews. So we're going to do AES, and we're going to make take the shared secret, and I'm not going to bother adding a salt. You could, but I take the shared secret, I'm going to run it through 1024 iterations of SHA-256, and then extract a 16-byte key from it. That's what this does. This is password-based key derivation. You generate a key out of anything. I'm going to treat the shared secret like a password, and so I get a key, starting with F8. And that's the key. I can now encrypt stuff with AES. So here's some clear text to encrypt. Just using post-quantum cryptography, and I chose it to be exactly a multiple of 16 bytes, although it's probably not necessary since I'm doing Galois counter mode. In fact, let's try that. I think I can add something here, like a couple more of these, and I think it'll be okay. Let's see. If it was, if it was electronic codebook mode, or CBC, it would complain and say the message has to be a multiple of 16 bytes. But Galois counter mode is like a stream cipher. It generates a bit stream and XORs with it, so it can be any length you want. So anyway, that makes a ciphertext, and now I can decrypt that ciphertext down here. And I want to use, oh good, I've already, so that's going to be this ciphertext. So now when I decrypt it, it's going to have the 3 exclamation points, and so it does. Okay, so anyway, Now you got everything. This is the whole story. This is how you generate the key. These two functions are how you exchange it with the other person and get the shared secret. And now you just use a key derivation function to turn that shared secret into a key, and you encrypt and decrypt with AES.
So these are the 3 steps, basically.
That's it. Yeah, and underneath these functions are that baffling lattice calculation stuff in high dimensionality, but they've written it up in the library. You don't have to worry about it. You can just use this library, and it works. That's why it's not any harder for a developer to implement the better cryptography. You just need a good library. And that's why it shouldn't be too hard for everyone to upgrade to this. The only thing is the keys get kind of long, but they're not horrible. Now, the keys are longer than might be useful. Like we said, the key was the 800 bytes and 1632 bytes. So that's longer than like RSA keys, but still that's not terrible. Anyway, and so I made a challenge here. What I found out, I looked at the library and I saw that there was a function to set the seed. So this is interesting. Now let me point this out. If I run this and I derive, I derived a shared secret. The shared secret starts with 95. If I just run it again, it creates a random number every time. So the shared secret will now be 6C. Every time I run it, it'll have a different shared secret. It's feeding in a random number from Alice. Now, that's fine for real work, but for projects where I want to have a flag, that's not okay. And I noticed, we're looking at it, that there is something called set random number seed. And I looked it up. It took a while to play with it. What you have to do is, I thought I could just give it a number, like 1, but you have to give it 48 bytes. So I'm giving it 48 zeros. And that did it. So now if you do that first, now it will no longer be random. I've set the seed, so it will always, it's pseudo-random number jitter, starts at this value. So now you get the same answer every time. And you took the machine learning course. We did this all the time there for the same reason.
Right, but you set the seed and you get the same number. It's still random, but it's repeating the randomness that you already...
Yeah, well, technically it was never random. It was always pseudo-random.
Yeah, pseudo, yeah,
but it had some kind of random-like seed from the time or something. And now I specify the seed, so it will create a predictable series of random numbers that will always be the same as long as you start from the same seed.
Right, yeah,
that's right. That's why, what you really should do is seed it from like the clock or something. But in this case, I seeded it with fixed value 0. So now I get a shared secret with 888. And if I run the same thing again, I'll get exactly the same answer because the random numbers are all the same every time. So, yeah, so that's why, so I put it down here. I say, do this, and now your shared secret should begin with 888. And your AES key should start with CC, so you'll know if you're on the right track. And then you'll be able to decrypt that and find the flag. So it should be pretty easy. You just have to do what was above there. And that's it. It's the new modern encryption we can all use. And you don't, now if you do Prod 800 we talked about last time, this is where you actually get into the math. And this can be kind of mind-boggling. You have these matrices full of polynomials that you're multiplying. That's what's really going on. But you don't need to know that to use it.
So when you say the encryption model may be safe, but then the implementation may lead to disasters.
Yeah.
Give me an intuition of bad implementation, for example, even using a metaphor. No?
Well, no, I do know. For RSA, I know which ones got cracked. OpenSSL used RSA encryption, and it was normally coded. So the flaw there was, if it makes an error while calculating and drops 1 bit, that has a non-random effect on the output. So the attack there I saw was they lowered the voltage of the power supply to make the processor make errors, and they encrypted something 1,000 times, and 100 of them were errors, and that was enough to deduce a 1024-bit key. And so computers do have an error rate. So that's one thing that can go wrong. Another thing that's always been around is a timing attack. From the time it takes, you can deduce something about the key. Another one is the radio emitted by the processor. Another one is the power consumed by the processor. All of those can leak out information. In fact, it's hard to write anything that doesn't leak out information by one of those channels.
So you're saying that some of these mistakes are unavoidable, some of these glitches?
There are, but they have been weaknesses many times in the past. They can avoid them by having a special chip that always takes the same amount of time and the same electronic crash to go through, and you can write constant time code that never takes any shortcuts. So it always takes the maximum time. and that will help fix that one. But emissions turn out to be almost impossible to stop. That was what the Tempest project found out decades ago. They found out that all these computer equipment and your monitor and everything are sending out radio waves that include information, and the NSA found the only thing you can do is work in like a windowless basement with metal all around. That's about the only thing you can do to be safe from that. Because all these emit radio for everything they do, and with a big antenna you can pick it up from some distance away. That's kind of an intrinsic flaw of all electronics.
So then, if I'm understanding correctly, the part of the solution for all these glitches can be either software program or hardware.
Oh yeah,
Because
or even just environmental, putting a cage outside.
Outside.
And also, you have to prevent unauthorized people from entering the server room. So locks and a security camera and access cards. That's why, all these aspects of security are interrelated. If somebody could sneak in the room, they could just watch the keyboard and find out what you're sending before the encryption gets in. So that's the thing about security. There's always a way to steal whatever you have.
Is it true what we see in movies sometimes that they're able to collect the fingerprints on the keyboard?
Oh yes.
So then they try the different combinations?
Oh yes, I've seen that. I've seen pins. A friend of mine used to work at a museum, and they had a pin code, and they didn't replace it, and you could just see which ones are worn out. So now you didn't get the order, but you could see. You should lower the number of guesses to a small number. And
because usually there are 4, 5, 6.
And I think if you actually took like an infrared camera and took a picture right after somebody did it, you could even get the order, because it'll take a while to cool off. So the hotter one will be the last one. And I think you can even do it with an iPhone. That's why, this is why physical security is a big part of it. And authenticating people is a big part of it. I say it's, all these things are related. And so there's no perfect security. The math can be very good, but there's always some way to get it. Like you can just bribe people to hand you the secret, Anyway, so I'm going to stop this recording.